Okay, admin of code day 14. We're now more than a day over halfway, which is kind of wild. Okay, bit mask, something something. Okay, looks like we've got some string parsing to do. Okay, so we have a bunch of things, either mask equals something or mem of something equals something. Great. Okay, so ignoring line, write the value to address blank. Okay. Specifying the bit mask. 2 bits in every written value. Okay. Gotcha. All the values left in memory. Okay. Excellent. So let's have our mem is equal to the nice map, and let's figure out how to parse out our stuff. So the parsing the bitmap's going to be interesting. Yeah, I'm not sure exactly how that's going to go. Like, I can do it logically, I just don't know how to. Okay. So the bit mask just says, hey, this is actually how things are going to go. Okay, so let's start by parsing out our things. We might actually just want to parse it as we're going. So for line in L, tokes is equal to line dot split, and we're going to split on, oops, the space equals space, and then we want if tokes of 0, and let's say mask is equal to I'm not sure how many characters that is exactly. Okay. Yeah, well, just mask is equal to nothing. Well, actually, let's just, yeah, that's a fine idea. Let's just copy this. We can just say it's quote because it's going to get written immediately. If tokes 0 equals mask, tokes of, or mask is equal to tokes of 1. Else, mem look is equal to, and it's going to be tokes of 0. I'm going to index on that from 0, 1, 2, 3, 4, from the 4th character through the second to last one. Print memlock. Double equals, not single. Cool, looks like we're getting the values we want. Let's just look at the beginning of it. So 24, 196, 3804, great, 432, yeah. Okay, we're getting that out the way we want. Mem location is equal to int of this. And then we want val is equal to int of tokes of 1. And now we need to figure out how to bit mask these things together, which is going to be fun. So I'm kind of thinking we just write a function to just do this manually, like as a string. So let's just write that def mask mask num. We're going to say num mask So let's say num bits is equal to stir of num2. Let's search this. Python int to binary string. What? That right there. Okay. And then we need to of val comma mask, and we're just going to print, oops, okay, that looks like it's doing approximately the right thing. I'm not going to check it right now. Well, I guess I could do print mask num of, or actually we don't even, just mask num of, and let's just say 2, empty string. Great. 4, 40. Great, that's what I want to hear. Well, want to see, I guess. Okay, so we've converted it into a string. Now we need to prepend zeros to it. To make it the same length of the mask. Or we could just go from the ends of the string to the beginning. That could also work. But I don't really want to deal with that. For num bits is equal to num bits, and it's going to be it's going to be 0 times how many zeros do we want? We want the length of mask minus length of num bits. Okay. Looks like we're prepending things the way we want to be. That's what I like to see. Okay, so we've now got num bits, and now we need to make the ands equal to that for c in, or let's see, for I in range length of mask. If mask of I equals x, ands plus equals num bits of I, if mask of I equals 1, ands plus equals, or else ands plus equals mask of I. Okay, And then right here we need to return int of ans2 base. Yep. Masked is equal to this, and then what we want to say is mem of memlock is equal to masked. And then at the very end, we need to get the answer. And the answer is the sum of all the values left in memory. Print sum mem.values. A 401. Okay. For some reason, version 2 of the decoder chip doesn't modify the values being written at all. Instead, as memory address decoder immediately before value modifies the corresponding bit of the destination memory address. Is floating? Okay. Whoa. Whoa. That's a lot of X's. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, this still looks doable. Like if there were a ton of X's, I'd be like, well, we need to figure out some new way of doing this because there's no way that that's going to be brute forceable. But it might actually be. Okay. Okay. Alright, time to figure out part 2. Let's get rid of these print lines because they are taking up a lot of space. We've still got a print line somewhere. There we go. Okay, so let's paste all this. So memory is that, mask is that. Overwritten with 1. Floating. Wow, okay. So what I might want to do is write a new function that takes in a memory address and the mask and returns the list of memory addresses. Def mem mask mem. It's gonna be num mask. So we've already figured out some stuff. So this will give us all the bits at the correct length, and then we can do something similar here. Okay. Mask of eyes equal to 0. Answer. So yeah, let's just make this string that has the x in it, and then we can figure it out. So if it's x, or if it's 1, so it's really just 0. So if it's 0, then you're adding in the memory address. Otherwise, you're adding in that. Great. Okay, so now we need to convert this into something that produces the list of all the possible values. Which I think might be easiest to write recursively. Let's think about that for a second. Let's call def mask mem helper, and all we need is just the number, or numster, and what we want to do is break this down. So let's say, yeah, this actually makes sense. Okay, I think this is making sense. So we want to find the first instance of x, and we want to replace it with a 0. We want to replace it with 1, and return both of those. So, let me quickly Google Python first character index. Oh, that's not what we want. Let's just try index of. Let's comment this out for a second. Print index of, let's, seven. Great. Index 5. Great. That's what we want. 0, 1, 2, 3, 4, 5. Great. And what we want to do is part 0 is equal to mask mem helper of numster dot. So we want to take out the, we want to find the I is equal to numster dot index of x. What does this return if it's not there? Value error substring not found. I don't remember the exact, try except. Cool. Okay, so that's what we want to do. I is equal to -1. Try. If I equals -1, return int numster 2. Else, just add that to make that happy. Okay, so else. Well, we want this to be a list. Return part 0 dot. Well, we need a num stir 0 is equal to num stir 0 of I is equal to 0. Part 0 of, and then we want num stir 0. Part 1 is equal to mask num helper num, oops, stir 1, return part 0 dot con. How do you join two lists? Oh, it's probably just plus. Frickin' Python. Okay, so now what we want to do, that's our mask. And then mem location. This is going to be mask mem. And it's just going to be mask mem is number and mask, and it's going to be mem lock mask. And then mem for lock in mask mem of lock equal to val. I totally just blew away the part 1 solution, didn't I? Let's just control Z out of that. Let's copy paste this. Okay, we've still got part 1 working now. Okay, let's paste this. Get rid of that. Invalid literal. Oh, it's capital X. Haha! Does not support item assignment. Change it to a list and then fine. list of I equals 0. And we want this is equal to great. Let's get rid of our prints. Wow, okay. Huh, we did it. Cool. Interesting. Felt like we were like really reaching into the strings and like forcing them to do what we wanted. I'm not sure that I am happy with like how concise it is, but I don't really know what to do to make it more concise. Let's think about this for a second. So we got in the 400s for these two parts and did it in under half an hour, and the fastest people did it in under 16 minutes. I am interested in some methods that other people used to really leverage Python. I did have to look a couple things up that I should not have had to look up. Let's clean this up a little bit. I am really glad that we got things to work so quickly. Like there wasn't much troubleshooting trying to figure out how things were supposed to go. It just worked. And I'm surprised by how quickly part 2 runs, even with all the different x's. I wonder what I would have done if these strings had been more loaded with x's, because trying to iterate over that exponential number of memory locations would not have been wieldy, to say the least. You know what we can do to make this work a little bit better? We can join these two for loops and just have two different memory sets. Mem2 is equal to, and then what we'll do here is these lines are the same, it's only these lines that change. And then we want mem2 of lock is equal to val, and now we want mask mem of memlock. And this is going to be mask2, mask2. There we go. Okay, I do like that. That makes me happy that we were able to clean that up in that way. Because the way that the masks are tracked is exactly the same in both parts. So let's think about these functions here. So mask number, so we convert the num bits into a string that is the right length. We iterate through the string, and if it's an x, then we read from num bits, otherwise we read from the mask. Is there a more concise way to Honestly, I think this is pretty clean. There probably is some sort of Python-ism that allows you to just take each of those x's and instead of having them being an x, have them be the value from the other string, but I don't know if it's worth it trying to figure that out. For the mask mem, um, I just have this to keep it out of the scope, or outside, so the scope is the right thing. Actually, you know what we can do? Instead of this, we can just I like that. That's a nice cleanup. Okay, that's a little bit cleaner. Yeah, I think I'm happy with this now. Essentially what we're doing is we're taking the mask, folding it into the number, and making this new string where we have the floating ones, or the things that are definitely ones or zeros, and then we create every single possible combination. I kind of want to print out some of these masked twos. It's just going to print a lot of stuff, but just to get an idea of what's going on. These are huge lists. Yeah, so all of these get spit out by one little call to that function, and it just tries flipping all those different bits and then sets all of those memory addresses. It's amazing how much work the computer can iterate through so quickly. Great. Well, I think we have our solution for today. I'm going to get this posted, and thanks for watching.